In this lecture, we're going to be talking about the biophysics of vision. So this is a chapter that's highly focused on geometrical optics, as well as the different rules and laws that come with this background. We're going to start first with a little bit of introduction as to what light is, and then hop into some important equations that we'll use to try and determine um, different aspects of vision in the human eye. So in this lecture, we'll first go through a recap of Audition, which we talked about in the previous lecture. Afterwards, we're just going to head straight into an introduction to vision and light. So we'll start off by figuring out what the different properties of light are, and then we'll go through some geometrical optics, especially if you haven't taken any geometrical optics before. This would be a really important few slides to cover. We'll be talking about refraction, basically the bending of light when it hits a different medium, and Snell's law, which applies to refraction. And then we'll take a look at thin lens equation and refractive power. Once we have that knowledge, we'll be able to apply that to optics in the human eye. So essentially, we're trying to figure out some sort of model for the eye so that we will be able to apply the equations and figure out some sort of parameter that we can use for further studies. So without going into those models, we first have to be able to understand the anatomy of the eye. So starting there, we'll talk about the retina, we'll talk about the photoreceptors and rods and cones, and then we'll talk about something called the reduced eye model and accommodation. So those are probably the two most important concepts to know for the biophysical modeling of a human eye. And then, of course, we'll talk about the resolving power of the eye by looking at diffraction and resolution. Okay, so first for the recap, we talked about audition in the previous lecture. I'm just going to go through a quick recap of the key equations for sound-related concepts. We'll talk about how hearing works in humans, and then end off with a summary of the Doppler effect and echolocation. So some of the key equations that we learned in the previous lecture, it had to do with pressure waves. So a sound wave is a pressure wave, and it can be represented by the following equation over here. You also have sound velocity in air fluid, as well as sound velocity in gas. So just keep in mind that these two equations here and here are different. There's also sound intensity, so we did learn about that. Sound intensity is going to be given by the amount of power coming from the source and how much of that power is going to penetrate the surface area of a sphere. So that's going to be power per area that it penetrates perpendicularly. So we have P over 4 pi r squared. Another important aspect to keep in mind is that there's an inverse square law to intensity. So the farther you are away from the source, the lower the intensity. We also spent a lot of time trying to figure out another way to represent intensity. So if you don't have P or R, for example, and you're told to solve for intensity, here's another equation that you can use. Maybe you're given the maximum amplitude of the wave, maybe you're given the frequency, the density, and the speed of the wave as well. So in that case, you might want to use the intensity equation with respect to pressure displacement. There's also another intensity equation with respect to just pressure. So you can use P squared over 2 rho V as well. Another equation that's very useful to remember is just the wavelength equation. So that's V equals to frequency times wavelength. So in terms of the anatomy of the human ear, you will have to know some of the anatomy. We did talk about the outer ear, the middle ear, and the inner ear in quite a bit of detail. So I would familiarize yourself with the key points in each one. I would also recommend familiarizing yourself with just the big picture. So when you listen to something, or when you're trying to hear something, sound waves are going to enter your ear canal. So let's say the sound wave is over here, it enters your ear canal, and then it travels towards the eardrums. The sound waves are going to cause the eardrum to vibrate right here. And at that point, we're in the middle ear. There are tiny hair cells that are inside the inner ear, inside the cochlea, that are going to convert these vibrations from the eardrum into electrical impulses and signals that are going to be picked up by our auditory nerve, and then gets the signal sent to our brain so that we can process what we're hearing. So just keep that in mind. The vibrations are going to start at the tympanic membrane. They're going to be amplified significantly as it goes through the middle ear towards the inner ear, and then the hair cells are going to receive those vibrations and create an action potential that gets sent to our brains. So once we get to the hair cells, another important aspect to know is, or to remember, is that the outer and the middle ears are going to help amplify a signal by almost a factor of 100. You should know where that factor of 100 comes from, or approximately 20 decibels under optimal conditions. And after that, it allows us to hear things. So these hair cells that just, I like this SEM image. So essentially just remember the hair cells are going to convert your vibrations to signals, and that neurotransmitters are going to be released to your nerve for the action potential. The last thing we talked about was the Doppler effect and echolocation. Most important equation is the Doppler effect equation. So if there's an observer, receiver, and a source, then you can use this equation to determine what the frequency is of the observer, or vice versa. In echolocation, animals are going to emit calls to the environment and listen to the echoes to locate and identify different objects nearby. Every animal has its own unique call, so it emits a different sort of frequency that's specific to their species. So for example, with bats, I believe they can go up to 300 or 400,000 hertz, but they can send out these sonar waves and then receive a bounce back signal, and then echolocate their location. So let's start off with an introduction to vision and light. We'll first talk about the science of vision, basically what is actually involved in vision itself. Talk about the wave nature of light, and then a little bit more about the wave nature of light. Since we're taking a look at waves, we should take a look at the polarization of light and something called birefringence. There also is a wave-particle duality to light. So light isn't just a wave, it can also act as a particle. So we'll take a look at the particle nature of light as well. And because of that, we can take a look at light intensity. Okay. So when we talk about light, we think of it as an agent that helps us see things. Light itself is going to be invisible, but its presence is going to stimulate our vision of other objects. So now our goal is to figure out how. So that means we have to combine our knowledge of human anatomy, or eye anatomy, with the physics of optics. So optics itself is the science of vision. Modern views state that light is a continuous flow of energy with a dual nature. Electromagnetic waves as one, as the wave part of light, and a stream of photons or particles as the particle portion of light, or particle nature of light. So light itself is used to describe the visible spectrum of electromagnetic radiation. So when we talk about light, it's usually something that we can see. So that means that light has to have a limit based on our thresholds. So if we talk about physics and optics, the physics of vision is going to focus on, number one, the nature of light, which is what kind of light is emitted by objects. And then we'll have to be able to take a look at the interaction of light with matter, as well as how it interacts with the physiology of the eye. Once we understand that, we'll be able to put into detail how light strikes the eye and how vision is excited. Once again, similar to audition, as soon as we receive some sort of signal from our eyes, we should pass that signal on through our neurons towards our brains. So first of all, we're going to tackle the wave nature of light. Light is basically a wave with a continuous flow of energy. It bends around obstacles through diffraction. And also, another very important aspect is that if it does enter into another medium, it refracts. So when we talk about light and eventually in our eyes, we'll have to realize that the light is going to pass through our eyes, through several layers within the eye, in order to reach our retinas. So we do have to understand refraction in order to figure out how much of that light is being refracted at each of those steps. Light combines with light waves, and that means that it can cause constructive or destructive interference. And most importantly, how do we characterize light? Light is going to be characterized by speed, wavelength, and frequency. So this formula should be quite familiar already, similar to the wavelength equation, just rewritten so that it's C equals to V times lambda, where V over here is frequency, and C is just the speed of light. So we have the speed of light being equal to the frequency times lambda. When we talk about light, remember we were only talking about the visible spectrum that we can see, because if it's outside of the visible spectrum, we won't be able to see it, and we don't regularly categorize it as light. So our eyes are sensitive to both wavelength and intensity. What we call visible light is between 400 and 750 nanometers, so the rainbow of color. You'll see that the portion of visible light is just a thin sliver of the entire possible range of different wavelengths. Of course, some wavelengths are going to be dangerous. You have UV light over here, you have X-rays, you have gamma rays as you get smaller and smaller in terms of the wavelength. You also have, as you increase your wavelength, you get infrared waves as well as radio waves. Now that we're talking about light as a wave, we should remember from our previous study in our audition that any wave can be represented by a sinusoidal function. Essentially, light waves are electromagnetic waves, and you can kind of see the sinusoidal nature of the wave over here. But because of the way light is, what light does is it contains a changing electric and magnetic component. So natural light is generally what we call unpolarized, as all the planes of propagation are equally probable. But when we do talk about the polarization of light, it means that we're forcing it to exhibit a certain property, either to make it linear, make it rotate at the same magnitude, at the same speed, or keep it at an angle permanently. So an electromagnetic wave can be polarized in the direction of its electric field. So over here in yellow, we have the electric field, and in red, the magnetic field. And the light source is here, and it propagates the photons across the wave. So there are three different types of polarization you should know about. There's linearly polarized, there's circularly polarized, and there's elliptically polarized. Just understanding the difference between them would be good enough. I'll go into a little bit more detail about each of these, but just keep in mind, you just have to know what the difference is. So linearly polarized is exactly that. It's linear. It only happens when your electric field oscillates in one plane in space. So that means I'm forcing all of my electric field to be just in one dimension, essentially, or 2D. Circularly polarized light is when your electric field rotates with a constant magnitude. So no longer is the wave propagating this way, but it's also rotating at the same magnitude. So it looks like it's spiraling in like a corkscrew. If you're spiraling in like a corkscrew, there are two different options. You can either spiral towards the right or you can spiral towards the left. So there can be clockwise or counterclockwise rotation. So for circularly polarized light, you can have right circular polarization or left circular polarization, depending on whether it's clockwise or counterclockwise. Last but not least, there's elliptically polarized light. That happens when the electric field will rotate with changing magnitude. So even though it does rotate, for example, like that corkscrew going in, it may have a different amplitude. So you get that elliptical structure. So it kind of looks like a slanted wave. So just so that we can visualize this, there are 3 different diagrams here. If you click on the YouTube link, you'll actually be able to see them in motion. But for linear polarization, you can see that we're forcing everything to be on one plane so that your light only travels in the up and, let's say, not really the X and Y direction, but supposedly the X and Y direction tilted over here. In the circular right-hand polarization, we can kind of see it's in the clockwise direction. So can't really see it unless you look at the video, but it's spinning this way. And so it's spinning this way towards the z-axis, or towards the positive z-axis, and it's going at the same speed. So what this is telling us is that it's just going around and around in a circle, and you form this circular ring. Now, if you take a look at an elliptical polarized light, you now have a changing magnitude. So maybe it's got greater magnitude over here and then less magnitude on the sides. Then you get some sort of elliptical shape of polarization, and we call that elliptical polarization. Okay, so continuing on with polarization, we should try and tie it back to vision somehow. So looking at polarization, some substances are anisotropic. What this means is that the properties of the material we're looking at, light in this case, depends on direction. Because we can have linearly polarized, circularly polarized, or elliptically polarized light, that has everything to do with direction because we're forcing things to be in certain directions or move in a certain way. So in that case, there are some substances that are dependent upon the direction of polarized light. So those types of substances are called optically anisotropic. So the word anisotropic by itself means that it depends on direction, but if you have optical anisotropy, it means that you have something that's dependent on the direction of light. So there are 2 common types of substances we can look at when we talk about anisotropy, or optical anisotropy. There are birefringent substances. So here I say it's substances that exhibit different refractive indices. The truth is, birefringent substances will have a refractive index that's fully dependent on the polarization and the direction of propagation of light. So that's what the definition of birefringent would mean. As an example, there are crystals that absorb more light in one plane than another, so that the light that progresses through the material will become more and more polarized as they proceed, and then end up having different refractive indices and causing bending of light to different degrees. Meanwhile, the other type of optical anisotropic material is called a dichroic material. So it exhibits dichroism. A dichroic material causes visible light to be split up into distinct beams of different wavelengths. Or we can also consider it to down here, I have another explanation for it. So number one, for dichroism, the substance has the ability to sense light polarization. Another way of looking at it is that the material has different absorption depending on light polarization and the orientation of molecules. So essentially what this means is that it can absorb light rays at different amounts due to polarization. And some examples are going to be your photoreceptors in our eyes that we'll be talking about later, shellfish, and of course lipid membranes. Both birefringence and dichroism are what we call manifestations of optical activity. Basically, optical activity means that a substance is able to rotate plane polarized light. It means that the substance has chiral molecules that will allow for manipulation of this. But for this course, you won't have to know about this, just have to know the big picture. So now that we've covered as much as we need to cover for the wave nature of light, we can now hop in to the particle nature of light. So light is basically a stream of photons that make up discrete bundles of energy. Planck proposed that radiant energy could exist only in discrete quanta, which are proportional to the frequency of each photon of energy E. So essentially there's an equation where the energy of the photon is equal to Planck's constant times the frequency of the wave. And because we do have another equation for the frequency of the wave, which was the wavelength equation, where C is equal to frequency times wavelength, we can replace frequency with C over lambda. So you get this as the equation for photon energy. Now, when we take a look at photons, they are going to be particles, and that means they are going to have energy that will either be emitted or absorbed. So when we take a look at light, we can also take a look at different fluorescent properties, which will come up in a later chapter. But with photons, you can absorb light and you can also emit light depending on different energy states of your particle. For now, that's all we need to know for the particle nature of light, because there will be a dedicated lecture for that later on. Apart from that, I want to mention that photoreceptive cells in the eye will be excited by a photon because the light is going to hit your eyes. That's going to signal a cascade reaction or a cascade of molecular reactions that will transmit a signal to your brain so that you can actually see and process what you've been able to visualize. The last thing I want to talk about for this section is something called light intensity. And primarily it just has to do with verbiage. Light intensity is given by the power per unit of solid angle. So what I want you to understand from this is that light intensity or luminous intensity shouldn't be confused with how we considered intensity back when we were looking at sound. With sound, we had the source having some power radiating outwards and penetrating the entire surface of the sphere. Essentially, that gives us what's called a flux measurement, which is how much of your power is passing through a certain area. This flux is going to be considered the total perceived power in all directions. So we have to consider the entire sphere when we talk about flux. Now we have something called light intensity. And in optics, when we talk about light intensity, it's given by a power per unit of solid angle, which means that this is a solid angle. It's just 1 unit. So we just want to see how much light is going through a specific area because we can focus light versus just look at how light radiates outwards. So the key difference is that Light intensity is not light flux. Light intensity is not comparable to sound intensity. We have light intensity expressed as something called candela, which is lumens per steradian. And 1 steradian is considered 1 solid angle over here. And you have an area of pi r squared. So light intensity, another way of considering it, when it says it's given by power per unit of solid angle, this whole term is also called luminous pointance, which we call candela. So we would consider this to be some sort of candela per unit of steradian. So with a general understanding of just the wave and particle nature of light out of the way, we can move on to some of the physical background and mathematical foundations that we need to know in order to tackle the biophysics of the eye. So let's first take a look at refraction and Snell's law. Like I said before, our goal is to be able to understand how we perceive vision and how we're able to see things. So that means light has to hit our eyes and go through our eyes to reach the back of the eyes called the retina. And that retina is going to process what we see and send a signal to our brain. So in order for us to understand how that happens, the first thing is refraction, because we are considering light going from air into our eyes. After that, there can be several issues if the refraction is not done correctly. So we're going to take a look at different aberrations or abnormalities. Outside of that, we'll also be able to take a look at refractive power, which I'll be able to explain in a bit. So if you've taken some optics, or if you've taken Physics 112, this should be quite familiar to you. This draws from that knowledge. Refraction and Snell's law. So refraction is when waves bend as they enter a medium. So let's say that this is medium 1 up here in white, and this is medium 2 below in blue. So there's going to be some sort of incident light that comes in and hits this interface between the two media. Now it's going to hit the interface at a specific angle to the normal, and then because it enters a new medium, it's going to bend a little bit depending on the refractive indices of the two different materials. And when it bends, it's going to bend at a certain angle called theta 2, also with respect to the normal to the interface. So you have the incident light and then the refracted light at the bottom. So as I mentioned before, the degree of bending is going to depend on the refractive index n of the medium that you're looking at. We can consider n to be equal to c over vm, which usually you wouldn't have to solve for. We would give you n. But the definition of n is given by this, the speed of light versus over the speed that the wave is at inside the medium. There's also, we also have to be able to figure out a way to determine what angle the refraction is going to occur at. And that's where Snell's law comes in. So Snell's law will actually relate the angle of incidence, which is theta 1, to the degree of refraction, which is theta 2. So we have n1 sine theta 1 is equal to n2 sine theta 2. In an ideal optical system, all the rays of a light are going to form a point. Whoopsie. So in an ideal optical system, all the rays of light from a point in the object plane should really converge to the same point on the image plane. So if I take a look at this image here, in an ideal system, all of my points should focus in on one focal point so that one image can form. But in some cases, aberrations or abnormalities can occur that causes the rays to converge at different points. In this case, you would have many focal points and end up with a blurry image because you aren't able to focus at a specific depth. So we first start with spherical aberrations, and then afterwards we'll talk about chromatic aberrations, because there are two different types that are the most important. A spherical aberration happens when the rays at different distances from the optic axis fail to converge to the same point in the lens with spherical surfaces. So exactly like this, you have a thin lens over here. You have incoming parallel light rays. You should have all the rays refract properly so that they hit one focal point. But in this case, seems like the center incident rays are focusing into a focal point that's a little bit farther away. So in that case, you end up with a blurry image. But there are ways to fix this. There's something called the GRIN eye lens. The GRIN just stands for gradient index, GR and IN. And that usually helps correct spherical aberration. So how does GRIN do this? What happens is that your pupil is reduced in bright light to reduce the spherical aberration, and in the darkness, your pupil is dilated to increase spherical aberration because you don't have to focus as much. Now, moving on to chromatic aberration, in optics, we have something called Cauchy's relationship. Basically, Cauchy's transmission equation is an empirical relationship that I've presented over here. You don't have to know it. It's an empirical relationship between the refractive index and the wavelength of light for a particular transparent material. So what we notice here is that your refractive index is going to decrease as your wavelength increases, and that's primarily what Cauchy's relationship is. We then take a look at chromatic aberration. And so that chromatic aberration is due to a different amount of bending for each color or each different wavelength. It's caused by dispersion, and because of the different focus of color in different places, you end up seeing just different fringes of color around the boundaries. So here, I have another thin lens. We have parallel light coming in at the top and bottom. What we expect is for everything to converge at one focal point, but in this case, because of the different wavelengths, it doesn't. And that's why we call it a chromatic aberration, because it separates the colors by focal point. So just know the difference between what chromatic aberration is and spherical aberration. When we take a look at refractive power, we do have to take a look at different types of lenses. There are two types of lenses that we should understand. There's a converging lens or a convex lens, and there's also a concave lens or a diverging lens. So just looking at these two diagrams, you have a parallel incident light going towards the lens. If you have a converging lens or a convex lens, it's going to refract inwards and converge to a focal point. Whereas if you have a diverging lens, it's going to refract outwards. So let's consider a curved surface between two different media. The light from the object in front of a convex lens, so right here, is brought to a focal point of the lens, a fixed point behind the lens. That's half the radius of curvature. Gauss's formula relates certain different things, parameters with each other, and you end up with this equation here, where you have the refractive power being equal to the refractive index of the first medium divided by your object distance, plus the refractive index of your second media divided by your image distance. So just keep in mind this is the equation for refractive power, and it'll be handy later on. For this course, you won't be expected to draw any of these diagrams for geometric optics. All we really want is to be able to get to a point to understand how vision happens in the human eye. So we have one equation already. The most important equation is actually the thin lens equation. So like we had before, we had N1 and N2. What happens if we have a lens with different media? For a thin lens, the thin lens equation will hold. So you have 1 over object distance plus 1 over the image distance equals to 1 over f. Let's now try and define what O, I, and F are. So let's say I have my converging lens here, and if it's converging, it's going to be a convex lens. So I have an object here, and I have some incident light coming towards my converging lens. I have a focal length f, where this light is going to go past the focal point and keep extending. Wherever all of these beams intersect, or refracted light intersects, you're going to get an image behind the lens. And if the image is behind the lens, you have an image distance. You have an image at an image distance I away from your lens, which we consider to be the origin. The object distance is simply how far away your real object is from the convex lens. So when you're doing calculations using the thin lens equation, just keep in mind where O is, what I is, and what F is, because F is not the frequency. Now, the next thing to understand is power itself. There is a thin lens approximation from Gullstrand's equation, which I've kind of highlighted here in gray. I've kind of dimmed it out in gray, because the thin lens approximation assumes that this term is insignificant or close to 1. And so, it's insignificant. So when we take a look at different thin lenses that are stacked next to each other, the power of each of those surfaces can just be added together and summed up. So if we want to consider, let's say, the refractive power of the human eye, let's say that we can break up the human eye into 4 different thin lenses, then we can say that the total power is equal to P1 plus P2 plus P3 plus P4 to get the total refractive power. So that's a very handy tool and trick to have when we apply it to the human eye. So we've gone through a couple of concepts that are related to geometric optics, as well as just understanding what light is. All of that background is more than enough for us to try and understand the optics within the human eye. So the first thing we want to do is figure out what the human eye actually looks like, break it down as much as we can, and simplify it. We'll then talk about refraction and the refractive power of the human eye, and see if there's a way for us to come up with a good model for the eye, because the eye is so complex. There are so many different components. As biophysicists, we do have to consider a dumbed down or a simpler version in order for us to apply certain equations. So we come up with something called the reduced eye model, and through that, we'll also be able to discover or learn about something called accommodation. Afterwards, we'll talk about retina and photoreceptors, as well as the resolving power of the eye and diffraction. So the last part of it really has to do with resolution. So in the human eye, light is going to travel through 4 specific media before reaching the retina. So it travels through the cornea, which is over here. We can kind of take a look at the eye here. Let's assume that the light hits the eye over here at the cornea. It's going to have to go past the cornea, and then it's going to have to go past the aqueous humor or vitreous humor, and then it's going to right here, and then it goes through the lens, and then it goes through the vitreous humor. Skipped one. So 1, 2, 3, and 4 before it hits the yellow retina at the back. So that means that if we have 4 different media, we potentially have 4 different refractions happening. And if we have a refractive power, we could potentially calculate the refractive power of each of these separately and then add it up to get the total refractive power. So that's exactly what we're going to try and do. One of the good things is that the refractive index of each of these media are going to be similar. So the greatest bending will take place between the air and the cornea. The lens itself that we have here is considered a gradient index lens, or GRIN. This is because the refractive index of the lens is not uniform, but has an average of 1.4. And the highest refractive index is going to be located at the center. We'll touch on this a little bit later. Okay, so remember, our goal is really to try and simplify everything. But before we can simplify something, we have to do the proper steps to be able to make an assumption. So from what we've learned in the previous slide, we know that there are 4 surfaces in the human eye that we have to consider. It means that there are 4 refractive powers that we have to consider. So we're actually capable of calculating these refractive powers using the equation we had before. The refractive power between the air and the cornea is going to be about 47 diopters. Between the cornea and the aqueous humor, you have about -5 diopters. You have the lens itself being about 7 diopters and the concave portion being 11 diopters. So the power of the eye lens over here and the cornea, using the thin lens approximation, we end up being able to get the total power, the refractive power of the cornea, because the cornea has both the air and aqueous humor. So you add the two up and you get 42 diopters. Now you have the refractive power of the lens. And so the refractive power of the lens includes the convex and the concave portion. And so you add the two together and you get 18 diopters. So the total power of the eye, just through this whole area, is going to be 60 diopters. So if I have the total power of the eye, and I already have a number for this as 60 diopters, it probably is a good idea if we can simplify the 4 different refractive powers into just one simple model. Instead of the human eye having 4 surfaces, what if we just assume the human eye had one lens with a total power of 60 diopters? So that leads us to what's called the reduced eye model. It's basically when we consider all of the refractive surfaces of the eye, and we replace it with one lens with a total power of 60 diopters. To us as biophysicists, this is much easier to work with because we're making a good assumption based on good data. So this equivalent lens is assumed to have a refractive index of 1.34. So just using that and the refractive index, we're able to make certain predictions based on this reduced eye model. So let's do an example here. When the eye is focused at a far point, not a fair point. So basically when the object distance is almost to infinity, your image distance is going to get really, really close to your focal point. So when I is equal to f, you have 1.34 divided by the power of the lens, and you get approximately 22.5 millimeters. So this isn't an equation or a value that you have to remember, but the idea is that you are able to use the reduced eye model to solve for different aspects of optics. So the optical center of the reduced eye lens, what we can assume is that it's 22.5 millimeters away from the retina. So moving on, we want to talk about something called accommodation. Accommodation is the ability of the eye to adjust its refractive power by automatically changing the eye's curvature of its lens. So the lens itself, before we had mentioned that the lens itself has different areas with different refractive indices. The lens is very special because it can adjust itself, and it's suspended by certain fibers attached to ciliary muscles so that you can make accommodations to put things into focus. So the key thing is that when we talk about accommodation, it's how the lens is able to adjust its refractive power and its completely controlled by the ciliary muscles of our bodies. So when the muscles are relaxed, the tension in your fibers, so this is the relaxed stage, when your ciliary muscles are relaxed, the tension in the fibers are going to stretch the lens and flatten it. In this case, a larger R is going to reduce your refractive power, and the eye will be able to focus more on distant objects. Now, when your muscles contract, the tension reduces and the lens is going to bulge up a little bit. This means a smaller radius of curvature is going to increase your refractive power, and then your eye is going to focus more on nearby objects. So just remember what happens if you want to focus on something that's nearby or far away. So you should know that if you are relaxed, then the lens is going to be more flattened, and then allow you to focus on farther objects. And if it's accommodated or contracted, it's going to have its ciliary muscles contract and then create a smaller radius of curvature to increase your refractive power. And of course, when we talk about refractive power, there are times that we're not perfect. Maybe we get old and we have an eye that fails to focus distant objects because there's a refractive error. So there are two very common refractive errors, which is why most people have glasses. There's myopia and there's hyperopia, essentially nearsightedness and farsightedness. So if you're like myself, I'm nearsighted, so that means your light is going to be focused more in front of your retina. So the light doesn't really reach exactly at your retina so that you can put things into focus. You need some additional help to correct that through another thin lens that can help adjust this. So by putting some glasses on, like myself, I'm able to focus on something that's far away. So this only happens for objects that's far away. If it's close, I don't need my glasses. And the main reason for that is because the focal length is too short. Now, if you have farsightedness or hyperopia, what happens is that your light is focused behind the retina. So like one of my family members, she is farsighted, which means she can't see anything up close, but she can see everything far away. So it means that she needs a corrective lens over here, and note that it's going to be a convex lens to help correct and help the incident light rays converge more closely to the retina. So speaking of the retina, we should probably take a look at what it actually involves or what it has. The retina is considered a light-sensitive tissue lining the back of your eye. So it's at the very far back. This picture is a zoomed-in picture of the retina, which showcases special cells called photoreceptors. What happens is the retina sends light as electrical impulses to the optic nerve, which then leads to the brain. The optic nerve is made up of millions of nerve fibers that are going to be able to, so the optic nerve here, is made up of millions of nerve fibers that are going to be able to transmit impulses to the visual cortex of our brain. Now, what are these signals that are being transmitted? They all come from these special cells called photoreceptors. So your rods are going to perceive black and white vision, and that gives us night vision. Your cones are going to perceive color and provide central vision, or what we call detailed vision. You should be able to also understand what photoreceptors are structurally. when we take a look at photoreceptors, there's something called rhodopsin. It's the light-sensitive pigment that is in rods. It's a transmembrane protein with something called retinol as its light-sensitive part. So there's rhodopsin, and it has some protein that has retinol. When exposed to light, this retinol changes from cis form to trans form and unbinds from scotopsin. So what's happening here is that there is a change in structure every time a photoreceptor is exposed to light, and that means that you'll be able to generate a signal to your optic nerve. Specifically, when we talk about rods, they're going to be more sensitive to light intensity than cones. Remember, cones have to deal with color, rods have to deal with light intensity. So when we talk about that, there are two types of vision we have to understand. There's scotopic vision, which helps resolve dark and light. Rods involves scotopsin during excitation. You also have photopic vision that resolves colors. So your rods aren't going to resolve colors, but your cones are. And so your cones involve not rhodopsin, but rather photopsin during excitation. Finally, we can try to make analogies for photoreceptors. And one of the closest analogies we can use for photoreceptors is that of fiber optics. So if you remember from the drawing previously, your photoreceptors are pretty long. And when we take a look at long objects that refract light, we can consider them a really long tube or a wire that refracts light. So right here, we said rods and cones are long, thin structures with photoreceptor molecules packed inside, and we can assume that they are long, thin cylinders. So light is going to travel through these structures, similar to how a light ray hits the walls of of a fiber optic cable and just bounces around in its core. So an optic fiber or waveguide has a transparent core of a refractive index N1, and it's surrounded by a medium of lower index N2. Essentially, what is happening is that your light is going to be trapped by a condition called total internal reflection when theta is greater than the critical angle. So won't talk too much about this because it's outside the requirements for this course, but essentially you have a critical angle that's reached for total internal reflection, and so that allows your light ray to be trapped and to bounce within the cable without escaping the fiber optic. So photoreceptors, as an analogy, can work as optic fibers since the internal refractive index is higher than the external refractive index. So the last two parts really have to do with how we can resolve things with our eye. What are our limits of resolution and what can limit our resolution? So the resolving power is the eye's ability to distinguish two separate points of small distance. So how close can two things be before they become one to our vision? So the better you can see this, the more the better your visual acuity. So what is resolving power defined by? It's defined by three things which you do have to know about. It's defined by spatial distribution of receptors and their diameter. So if your photoreceptors are separated, you do get better resolution. The closer they are, the worse it gets. It's defined by the focus of the eye lens. It's also defined by the diffraction by the pupil. So the pupil is a small aperture in the middle of your eye where light can be diffracted and spread by your eye lens. So explaining a little bit more about diffraction. Diffraction is when light bends at an obstacle's boundaries. So as a wave, your light is going to pass through a small circular aperture and diffuse into an airy disk surrounded by, so these are airy disks, surrounded by fainter concentric circular rings. So we consider this some sort of smearing. If the smearing is greater than that of the aberrations of the system, then the imaging process is said to be diffraction limited. So if there's too much smearing, then that means you're limiting some of the resolution. In terms of being able to figure out the limiting resolution of a system, we fall back to something called Rayleigh's criterion. So Rayleigh's criterion states that when the central maxima from two distinct objects fall separately on the retina, the objects can be resolved if they do not overlap. So over here, there is some overlap, but it says the central maxima should not overlap. Here, there are clearly two central maxima and they don't overlap. Even though the airy disks do overlap, the two peaks do not. Over here, the two peaks do start to overlap, and at that point, you wouldn't be able to tell the difference between the two. You can almost see that these two have merged into one singular airy disk. So let's try and present this mathematically. So this is a better picture. Took it from hyperphysics, but probably have the best example that matched the picture I had before. This is a fully resolved image. So you have a nice singular peak. Now you have Rayleigh's criterion, in which case you have two peaks. There's still two individual central maxima, so this is probably the bare minimum you can have in order to tell two things apart. And this is when they're so close that the airy disks have merged and you really have an unresolved object. So in order to try and quantify some of this, we know the diameter of the lens aperture, so we'll call that d. We know the wavelength of light, and we call that lambda. What we can do is find the angular resolution. So that means you can find theta is equal to 1.22 lambda over d. I won't derive this because it requires a lot more calculus than expected of you for this course. Apart from that, if you do have angular resolution, you can also solve for spatial resolution. And that spatial resolution is going to be in meters. So it's actually a distance measurement. So in most cases, you would just take this equation and be able to figure out what your minimum distance is in order to resolve the object. So what is the minimum resolvable distance between objects before it becomes 1? So L is equal to F times 2 times theta, or we can just say it's 2.44 times lambda F over dn. So just keep that in mind. These two are useful equations to have when we're working with resolution. So last but not least, now that we have these two equations, we should probably apply it to the eye. So when we're taking a look at the spatial resolution of our eyes, let's try and make our lives simpler. We'll use the reduced eye model and we'll apply these equations. So with the reduced eye lens model, we already know that F is 17 millimeters, the focal point. We know that the refractive index is 1, and we know that D is equal to 4 millimeters. So for lambda, or a wavelength of 550 nanometers, just randomly, we have a minimum spatial resolution of 5.7 micrometers. So this 5.7 micrometers are the diameter of our rods and cones are 1 to 2 micrometers. There's so many of them within the spot of central maximum. So that means that the more densely they are packed, the better the resolution. Now for some practice problems, just so that you can familiarize yourself with what types of questions we'd be asking you for. You should be able to calculate the accommodation of the eye in diopters. So just remember how accommodation is, Just remember how refractive power is calculated and then be able to figure out the change in accommodation. You should also be able to use Snell's law and find the angle of refraction. And you also should be able to determine the distance from the lens to a film or any other parameter from the thin lens equation. So we'll be going through these practice problems during the live lecture, and then that should be good enough practice for an upcoming quiz. So just as a summary, what should you remember from this lecture? So we did talk about different concepts and laws for geometrical optics. Those would be very important. So definitely understand the wave-particle duality of light, understand how to use Snell's law and calculate refraction, understand the thin lens equation and know how to use it, know what object distance, image distance, and focal point are, and of course, be able to calculate the refractive power. In terms of the human eye, we did talk about the general anatomy of the eye, essentially just understand what the 4 different barriers were in order for light to reach the retina, and the fact that we are able to combine all of those barriers into one thin lens with one combined refractive power, and that model is called the reduced eye model. There's also something called accommodation, and when it comes to accommodation, you should be able to apply the equations from the reduced eye model and be able to determine how much accommodation is required in order for a specific refractive power to be achieved. After that, we talked about some retinas and photoreceptors, definitely understand how they work, photoreceptors specifically, and also be able to understand any limiting resolution from the distances between photoreceptors. So apart from that, understand the big picture of how vision works, especially how we go from being able to see something and then having that light go into our eyes, into the retina, and then go through the optic nerve and into the visual cortex of our brains.